Okay, this is called Weirdness in the Logic of Lightspeed Invariance, and it's referring to the article called The Weirdness and the Logic of the Principle of Invariance of the Speed of Light, and it's at that link here. So we go to it now. Here we go. So, first of all, note it's from the University of New South Wales. This is sort of the typical thing of what is taught as relativity, and if you go through all the other pages in it, it's just loads of nonsense. But if we can pick up the nonsense from this page, it's a bit insightful. So we pause that a minute. On this page it's saying how weird is the invariance of the speed of light. Is the principle of special relativity really counterintuitive? In other words, it's not sensible. If we go down, it depends on how one expresses it and to whose intuition one appeals. So it's all just bluff, really. Right. For example, it does seem counterintuitive that the speed of light does not depend on the motion of the observer in our animation. The animation here above here, which is going on. Zoe turns on the headlights of her spaceship. She measures the speed of light from her headlights as c with respect to her. Jason sees her travelling towards him at, let's say, v. That's the velocity or speed in that direction of v. And he measures the speed of light from her headlights as c. No, not c plus v, but just c. So if it was Newtonian physics, you would be getting c plus v if v is non-zero. If v is non-zero, then c plus v would be bigger than c. But they're saying, making the claim, it's not bigger than c, it is c. And then it's pointing out the problem. Surely this is counterintuitive, question mark. Maybe even crazy. Surely relative speeds add up. Let's consider first two more familiar cases. And if we go through this, it's just all waffle, really. Again, Zoe travels towards Jasper at speed v. First, suppose that instead of light, Zoe fires an arrow from her car at speed u. This is Zoe here firing an arrow as she measured it. Jasper will measure its speed as v plus u, as predicted by Galilean relativity, and that's just basically Newtonian physics. So this is moving at v. This is moving at v in that direction, and the arrow is going at u. Alternatively, she sounds the horn. The sound will travel forward with the speed of v of sound with respect to the air that is the medium for the sound wave. In the absence of wind, Jasper will measure the sound to be travelling at v of sound, and Zoe will measure its speed relative to her as v of sound minus v, again as specified by Galilean relativity, which is basically Newtonian physics. And this is So both those cases are understandable. So it carries on waffling, here, and eventually you're going to get to the issue of what you're doing with the speed of light. So, having dealt with these two cases, it's now going to start to talk about light. It is tempting to extrapolate one or other of these results to light. If light is like little arrows, Jasper should measure V plus C. If light is like sound, and if its medium is stationary with respect to Jasper, then Zoe should measure its speed as V minus V. Now, wants to discuss the possibility of medium for light later. If we are really careful in our thinking, however, we should also say that light may be neither like arrows nor like sound. The extrapolation mentioned above is tempting, but it would be a huge extrapolation. Light travels nearly 1,000,000 times faster than sound, and extrapolations are always dangerous. For instance, very near where you are now, the temperature and other physical conditions are, I hope, fairly comfortable, but the further you go from your familiar surroundings, suppose for instance you go 20 kilometres up or down, the more likely things are to be different in surprising ways. Or if you go up 20 kilometres into sort of outer space, or manage to dig down 20 kilometres into the earth, the further you go from the familiar, the more likely we shall be surprised, and the speed of light is a very unfamiliar speed. So they're trying to make out that light speed is unfamiliar to you. Indeed, the speed of light, about 300,000 kilometres per second, is so great that our intuition's of little use. They're trying to persuade you to abandon intuition, which is basically common sense. All the observations about speed that you have ever made, all of the experience upon which your common sense is based, are in a teeny area of physical reality that we could label extremely low speed compared with light. So there you go. They're trying to get you to believe that light speed is different to the speeds you're used to. It is often the case that one can make approximations that apply over a limited region of reality, but that fail when we examine a larger range. For instance, objects fall at 9.8 meters per second in the lab, also in the basement or on the roof, but this is not true in high orbits or at the centre of the Earth. So they're trying to set up a bluff of trying to confuse you with other things, rather than to stick to the facts about how you're supposed to deal with velocities and speeds. Right, at this stage, many of my students say things like, the invariance of the speed of light among observers is impossible. Oh, I can't understand it. And this is where we get all the idea that Einstein's relativity doesn't make any sense. And my position is, it doesn't make any sense because it's nonsense. Well, it's not impossible, but going with him, he's saying, well, it's not impossible, it's even more possible, it is true. So he's claiming, although it may look impossible, it is true, and that's all. diverting you on away from the straightforward answer, but what you were told was nonsense, and it is nonsense. This is something that has been extensively measured, and many refinements to the Michelson and Morley experiment and complementary experiments have confirmed this variance to a very great precision. And really what they're doing here is misrepresenting experiments like the Michelson and Morley experiment, and I've gone into the maths on things like this, which are best basically using the maths from which the Michelson Morley experiment is using. Carrying on. As to understanding it, there isn't really much to understand. However surprising and weird it may be, it is the case, so he's trying to get you to believe it even though it's weird. It is the law in our universe. It's all just bogus. It's just trying to get you to accept something that is nonsense. The fact of the invariance of C doesn't take much understanding. What requires understanding are its consequences and how it can be interpreted into what we already know. And so now they want to pursue the logic, and it's all just nonsense. It's just this little bit here. They've tried to persuade you to accept nonsense. They're misrepresenting the Michelson-Morley experiment, making false claims about it, and trying to get you to believe nonsense. But let's pursue the logic. Can we explain why the universe is this way? In physics, explanations go deeper and deeper, but they have to stop somewhere. Laws of nature are basic building blocks. For instance, if you ask why the electric force follows an inverse square law, we can give a subtle explanation that goes one level deep further down in a sense. Gauss's law shows the inverse square law is a result of the geometry of the three-dimensional universe. So they're just bluffing you off, trying to throw you into another tangent, consider something else, when really you should be trying to concentrate on the fact that they're messing up velocity and speed. Some students will then say, very well, but I might as well just accept that it is an inverse square law and stop there. Similarly, we shall now go further with the principle of special relativity, because we can give some insight into why the universe is this way, but again you might find it more comfortable just to accept the invariance as a law of nature. And that's basically what they want you to do. They want you to just give up thinking about it. They want you to just accept it. And basically it's just all this nonsense they just told you earlier in the previous paragraph. They've told you a lie about the Michelson-Morley experiment. The maths from it, as I pointed out in this video, doesn't come out the way they do. They just got to mess up the maths. So if you decide to just accept it, you are just accepting nonsense. For physicists, the principle of special relativity seems elegant and almost necessary, even though most of us still feel that it is counterintuitive in some ways. So they want people to say, oh, it's nice and elegant and necessary, and even if you don't understand it, it doesn't make any sense to you. Being counterintuitive, it doesn't make any sense. They just want you to think, oh, it's beautiful, nice, elegant. Partly it's due to the familiarity that physicists have with special relativity, but mainly it's due to our familiarity with electromagnetism. But let's see how the principle of special relativity is not necessarily counterintuitive, but follows logically from the nicely intuitive principle of Galilean relativity. And of course it doesn't. No way does it do it. So we go into where they're really messing it up. So it's a typical thing. This is a typical little, stop it, this is a typical little thing they show you of somebody stationary observing something moving, and this thing is emitting light here from its headlights, and this person is observing this. Go forward. So there you go, that's moving. So, right. If we go into that. Right. So, in our animation, Zoe, this is Zoe here, that's Zoe, turns on the headlights of her spaceship. She measures the speed from her headlights as C with respect to her. So that should be quite simple. So Zoe turns on her headlights from there to there. She measures that the light speed is C. Jasper sees her travelling towards him at say V. So she's moving at speed V. So she's moving. He measures the speed of light from headlights to C. And he says it's not C plus V, but C. So where is he measuring it from? This is the whole point of the bluff they have suddenly given you here. If we move it closer. This is Jasper. This is Zoe. Light leaves her headlights here and goes forward here. Jasper observes that. But where is he measuring the light speed with respect to? If he takes that point there, well, for Zoe, that headlight is moving. That headlight moves on further. So he can take the measurement there, or he can take the measurement from as the headlight is moving forward. So the light is going from there to there. But him, is he measuring the light speed from there, or is he measuring it from where it moves to? And that's the whole point of it. With respect to what? Jasper measures the speed of light with respect to what? That, or what that moves to. So you can measure it from there to there, or he's taking into account, he's saying that he's measuring it from that as where it's moved to. If we can pick it up next bit. So that headlight was over here earlier and it's now moved to here. So if he's measuring the light speed from there to there, it's not going to be the same as the light speed from there to there. It's different. So that is the big issue. Where is he measuring the light speed to from? Is he measuring it from a moving point from which the light is emitted from, or is he measuring it from a stationary point? He's looking, you see in that point, original point earlier, it was emitted there, and it's moving. It's a completely different thing. So Zoe, she measures the speed of light from her headlights to C. With respect to her, this point is moving. She measures that as C. But him, he has the choice of measuring it from a stationary point or a moving point. So what's he doing? He measures the speed of light from headlights as C, but relative to what? Is he measuring that relative to a stationary point, or is he measuring that relative to a moving point? And it's totally different things. You say, well, that's the whole point of it. That is the whole total point of it. He's got a choice of two different things. If he's just seeing this move and he's measuring the speed of light from this moving point to here, as the whole thing is moving, that's not the same as if he's taking it from a stationary point. Two different things. And if he's measuring it C as it's moving and taking into account that Zoe is moving at V, then he's going to say it's C plus V. And that is straightforward Newtonian physics. You say, oh well, just a minute. They've got time dilation and they've got length contraction going on. Yeah. You go back to this video here. As pointed out in this video, this lecturer, he just starts from Newtonian physics. When he constructs his maths, he just does Newtonian physics. He's considering the light bouncing between mirrors in this direction, and it's moving that way. And that is using Newtonian physics. And this one, when you set up this, that is using Newtonian physics as well. When you first look at it, before you go on to all that other stuff about time dilation and length contraction, you're asking yourself, how's he measuring the light speed? Is he measuring the light speed relative to a stationary point, or is he measuring it relative to a moving point? Because she's got a moving point. If he's measuring the light speed in her frame, that's not the same as the light speed that you can measure with respect to a stationary point. If we pull it up here, he measures the speed of light from headlights to C. Relative to what? Relative to a stationary point or to a moving point? They don't say. This is just a typical example of how relativity is taught to people. They don't tell them the difference. It's just Newtonian physics really, And as pointed out in this video, all they do is mess up the maths. Really, all they're dealing with, they start as Newtonian physics. They start with a situation like this. Stop it. That is just straightforward Newtonian physics, deals with that. And where they can mess this bit up is they don't tell you whether he's making a measurement relative to a stationary point or a moving point. And by doing that, you can mess up Newtonian physics on this. So if you get down, go back to this bit. At this stage, many of my students say things like, the invariance of the speed of light among observers is impossible, or I can't understand it. No wonder. They don't tell you. They totally mess up this. Zoe's moving, he's measuring light speed, and they totally mess up how he's dealing with his measurement. No wonder students don't understand it. They just completely messed up their maths. Thank you.